All right, good afternoon, everyone. Welcome to EfficientML.ai Lecture 10. Today we are going to talk about MCUNet, TinyML on microcontrollers. So today we'll talk about what is TinyML, basically what is the motivation, the challenges of TinyML. You squeeze deep neural networks into these tiny microcontrollers. We're going to talk about how to design those neural nets very small that can fit those microcontrollers, and talk about several applications from vision to audio and also time series. Homework is due today. Hopefully you have a good experience with that, and we have office hour after the lecture to help you. So now let's start with what is TinyML. So as we can see, with the years going on, the model size is growing exponentially. So we need new algorithms and hardware for TinyML and Green AI. The goal is to achieve low energy, low latency, low cost, and offer better privacy for the users, such that we can run the machine learning applications locally on our devices. So from the cloud to the edge, we no longer have to upload the private data so that it can better preserve the privacy. So we have seen many AI applications on the mobile phones. What is the next big thing? What is the, can we go even smaller? So those are the IoT devices and microcontrollers. They are very ubiquitous. The amount of these IoT devices are growing very fast in the past couple of years. They are very low cost, just a few dollars. And also they consume low power, can be battery powered to reduce the carbon. Can be widely used in smart home applications, smart manufacturing, healthcare, and also precision agriculture. But it's not easy. If we compare the compute resource, the memory, the storage, it's tens of gigabytes, couple of gigabytes. But now, when we are going to IoT devices, just a few hundred kilobytes of SRAM and 1 megabyte of flash, which is a couple of orders of magnitude smaller compared with cloud AI and mobile AI. So we need to both reduce the weight and also the activations to fit those deep neural nets for TinyML applications. So we not only have this latency constraint and energy constraint like we had for mobile AI, but also those tight memory constraints, since we have only a couple of hundred kilobytes of SRAM and maybe 1 or 2 megabytes of flash to store those weights. So let's dive deeper about what is the constraint for the weights and activations with respect to the memory. So this is a neural network. We have the weights and also the activations. So what are they stored? Where are they stored? The input activation and output activation, we have to store them in readable and writable memory. Since this is not static, we have to refresh it, we have to change it layer by layer so that we cannot put them in flash. But for the kernel, for the weight, we can put them in the flash. By the way, for a microcontroller, it doesn't have DRAM, so it's just SRAM and also the flash. So flash is read-only on the microcontroller. So only the kernels, the weight, can store in the flash. And the activation, the input and output activation, goes to the SRAM. If you have the DRAM, that becomes the next level of memory hierarchy under the SRAM. So what is the typical size of the SRAM? This Adreno Nano, this microcontroller has 256 kilobytes of SRAM and 1 megabyte of flash. This STM32 F746 microcontroller has 320 kilobytes of SRAM and only 1 megabyte of flash. But so far, the model we described, like Ryzen 50, MobileNet, they are way larger than this constraint. So what does it mean for the weight and activations? The flash stores the weight. Okay, so the flash, the size of the flash concerns our model size. The model is static, no need to change. We don't need to hold the entire model when we are calculating each layer. And SRAM usage equal to the input activation plus the output activation for every layer. That is dynamic, since each layer we have to calculate a new activation. And we care about the peak SRAM, the largest consumption in any layer. Since weights are not counted, we can fetch them partially and then throw them away, and then we continue to the last layer, and we always have the flash as the back storage for those weights. So in first order approximation, the model size determines the size of the flash determines the model size. The size of the SRAM determines the input activation and output activation. So let's see what is the gap. Rather than 50, this is the peak SRAM usage for rather than 50 MobileNet V2 and the quantized version of MobileNet V2. There is still a 5x gap between what is available versus what we need. So the key question is, how do we reduce this peak memory so that it can fit the SRAM of microcontrollers? So the key question is, we want to not only reduce the model size, which concerns the flash, but also the activation size, which concerns the SRAM. Conventional work like MobileNet V2, compared with its previous generation, the ResNet, can drastically reduce the number of parameters, 4.6x smaller parameters. But the peak activation didn't decrease, but increased. We talk about this when we are talking about the inverted bottleneck. Right? Remember, what is the reason? The peak activation is actually larger from ResNet to MobileNet. That's due to the expansion ratio. Remember, we had a inverted bottleneck. The middle layer for the depth-wise layer has 6 times more channels than the input and output. Right? So that makes the activation, the peak activation, actually larger than ResNet. So only reducing the model size is not enough. We also need to care about the peak activation size. So MCUNet, which is proposed by G, not only reduce the model size, but also the activation size. So let's see how that was done. We developed 2 generations of MCUNets in 2020 and also 2021. So the knowledge we discussed today is very fresh. Both are highlighted by MIT News. Bring deep learning to IoT devices and solving the alleviates the bottleneck in the memory usage. So what is the landscape? So existing work, we talk about NAS, neural architecture search. So given the fixed inference library, we want to find the best model architecture that runs fast. Another line of work focusing on designing the inference library, like given different neural nets, ResNet, MobileNet, focus on developing the inference library, the inference engine. But we find, given such a tight constraint, neither of them is enough. Instead, we should co-design the neural architecture search algorithm with the inference engine altogether. So the neural architecture search gives a good neural architecture for the inference engine, which provide a very efficient compiler and a runtime to support such efficient models. So that's the key idea of MCUNet by using system and algorithm co-design. So we'll dive deeper into these 2 parts separately. One is the TinyNAS. The second part is the TinyEngine. Let's start with the TinyNAS, Tiny Neural Architecture Search. And in the next lecture, we're going to talk about TinyEngine. A little bit of overview of neural architecture search. Rather than manually design the model to fit a particular hardware constraint, we want to have this automated methodology to use machines to design machine learning models. And to begin with, a search space is very crucial for neural architecture search. Like we mentioned, in the NAS lecture, right? Given the full network space, there might be different subspaces that is better. But the search space for microcontroller is very rare. People previously has focused on like cloud and also mobile. There's no such prior design space for microcontrollers. So one option is, of course, we can reuse those carefully designed mobile AI's search space, like MobileNet, MNASNet, etc., for TinyML. But it doesn't work. Even the smallest subnetwork in the search space, even the smallest one, still cannot fit the hardware due to the huge gap of memory, 320 kilobyte versus 4 gigabyte of memory. So what do we do? We need to smartly pick a search space, a design space to begin with for IoT devices. And how do we do that? What is the design space here? We character them by the resolution and also the width multiplier. How wide is the neural network and what is the resolution? And the specific resolution and width can lead to a sub search space. And then we can talk about the number of channels, the kernel size, etc. For example, in the mobile AI scenario, using a resolution for 224 and width multiplier of 1.0 is pretty commonly used search space. And a scaled up space, like a larger resolution, large width multiplier, is good for GPUs. Maybe even for modern GPUs, maybe even a larger resolution is helpful. But for microcontrollers, which has drastically different memory sizes, what should be the correct resolution and width multiplier? So the methodology, like we mentioned, is to, given this memory and storage constraints, we first derive a optimized subspace and then perform neural architecture search on the subspace. And here in the subspace, we want to first determine the resolution with multiplier, and then determine the kernel size, expansion ratio, number of blocks, etc. So rather than putting everything together, we want to separate them into two stages. First, we narrow down a subset, and then perform search on the subspace, so that the search can be more efficient. And how do we determine if the search space is good or not? Whether we should use 224 resolution with multiplier 1, or we can use like a smaller resolution but larger with multiplier. Of course, we can train a model, get the accuracy, and then compare. But training a model is notoriously difficult, it takes a long time. So we want to use some approximation. What is the approximation here? Given a memory constraint, given the same memory constraint, a good design space is more likely to achieve high flops under this same memory constraint. Since memory is precious, that's the hard constraint. We only have this amount of SRAM and flash. But how can we squeeze more compute in this fixed amount of memory? And remember, computation is cheap compared with memory movement. So we want to maximize the amount of flops we can do, which is positively correlated with the model capacity. The larger the capacity of the model, the higher the accuracy. So use this as a proxy to estimate the accuracy without having to train it. Therefore, we tried a lot of different design spaces in different color here. For example, we can compare this black design space and red design space. What is the difference between them? Which one is better? So here, the x-axis is the flops, okay, and the y-axis is the cumulative probability. What's the percentage of the models can achieve this certain number of flops? So here, in the black design space, all the models are larger than 28 million flops. All the models. Well, in the red design space, all the models are larger than 41 million flops. So certainly, this one is better. Right? We can look at another point. So for here, 20% of the models are larger than 32 million flops. 32 million flops. Here is 80%, so 20% of them is larger than 32 million. The higher, the better. And you can see here, it's only a top 1/5 of the models is good. But here, the top 20% has more than 15 million flops, which is larger than 32 million, right? Meaning that the worst one is better than this. This top performing one is also better than this black design space. Overall, this red design space is outperforming this black design space. And what are they? So this red design space corresponds to with multiplier of 0.5, resolution of 144. What about the black? 0.3, much smaller width and slightly larger resolution. So let's dive deeper, try to see this configuration between different SRAM size as we are increasing the size of the SRAM from 192 kilobyte to 512 kilobyte. And here we also have a large design space for the flash, like different microcontrollers from $50 to $10. They can have drastically different resources from 512 kilobyte to 2 megabyte. And here is showing the width multiplier, the width of the model, the number of channels. And here is showing the resolution from 122 to 208, etc. So here we have three designs. Okay? 1, 2, 3. And here 1, 2, 3. Okay? So this point actually matches this point. They have the same amount of SRAM, 192 kilobyte. They have the same number of the size of the flash. But here we're comparing the width multiplier and also the resolution. Like in design 1, width multiplier 0.4, resolution 112. Design 2 with multiplier 0.3, resolution 208. So when the SRAM capacity increases but keep the flash the same, what happens to the width multiplier and the resolution? And why is that? What gets stored in the SRAM? Wait or activation? Now, activation stores in SRAM. Wait stored in the flash, right? So flash is read only. So when we are increasing the SRAM, the number of channels is actually staying roughly the same, because increasing the SRAM size, we can enlarge the resolution, since resolution determines the activation size, which is resolution times resolution times the number of channels. Right? But here the weight is like 3 by 3 times input channel times output channel. The flash stays the same, therefore the input channel, output channel should stay the same. So that's why you see in this direction, the number of channels is roughly staying the same for the optimal design. But the resolution is getting larger since you can store larger activation in the SRAM, since the SRAM increased. So that's from design 1 to design 2. What about from design 1 to design 3? So here we are increasing the flash. Right? The flash increased from 0.5 megabyte to 2 megabytes. But we are staying keeping the SRAM the same, like 192 kilobytes of SRAM. what is happening here for the with multiplier and also for the resolution. We can see here the with multiplier actually is getting larger.
Yes.
Well, the resolution actually gets decreased, right? So why the width multiplier is getting larger here? Because the flash increased, we can hold a much larger model here. You have more capacity, you have more flash to hold a larger model. Model size is basically like 3 by 3 times input channel times output channel. We can have a larger number of channels. That's why the width multiplier is enlarged. But why the resolution decreased? Because here the SRAM is staying the same, right? SRAM matters when you come to the activation. And activation is determined by resolution times number of channels. If the channel increase, the resolution has to decrease so that it can fit the same amount of SRAM for the activation. So these are the complications to help you understand the trade-off when you are designing the CNNs to fit SRAM and also flash. So after narrowing down the design space, we can perform this once-for-all architecture search to random sample subnetworks and fine-tune this model, get a subset of it like you did in the homework, and we can do evolutionary search out of this once-for-all network to find the best child network. So I will skip that part since we already covered that in the NAS lecture. So after all this process, we compare MobileNet v2 and the TinyNAS, which is our search model. What do we find here? We care about the peak activation memory, which determines how much SRAM we can fit. There's pretty big gap between MobileNet v2, but our search model, the gap is smaller. And it's more better utilizing the available resource. Like here, this channel, this activation is pretty small. This is pretty big, but our threshold should be here so that we can fit everything. So here, they are all wasted. But on the right-hand side, our model's distribution is flatter, so we are better utilizing this peak memory in this scenario. And using this approach, this is the latency versus accuracy trade-off. We can push the frontier 2.4 times faster than our 2019's result. This is 2020's result. And here is the peak SRAM usage versus the accuracy. It's also about 3.7 times smaller compared with the MobileNet v2, given the same accuracy horizontally. And this is the 256 kilobyte constraint on a microcontroller. So this yellow curve is clearly within that threshold. Is everything solved? So what is the remaining problem? So if we plot the distribution of the activation memory, we can still find there's pretty big spikes in the first couple of stages, and then the activation becomes very small. So that's a big imbalance. This is the 256 kilobyte of constraint on a microcontroller. This is the peak memory, which is 1,372 kilobyte, which is much larger than this 256 kilobyte of memory constraint. So everything after this layer 5, they can fit this constraint. But everything before this layer 5, they cannot fit. These layers exceeded the memory constraint. What is the reason this early layer has so much so large peak activation memory. Actually, it's the larger resolution. They all use like 3x3 kernels, so activation matters to the SRAM usage. Remember, we are doing down sample, right? Continue doing down sample. That's why the resolution gets smaller and smaller, and then the memory gets smaller and smaller. But here in the beginning, the resolution is pretty big. So ideally, if we can reduce the memory usage for this initial stage, then we can reduce this overall memory. So let's see how do we do that. As we just talk about it, the key reason is due to the large resolution. This large resolution in the first couple of stages. Once we downsample that in later stage, the memory becomes, every downsample make it 4 times smaller, right? So previously we do it layer by layer, like doing the first layer, and then we do it for the second layer. Okay, so every time when we are doing the first layer, we have to keep input activation, output activation, both of them in the memory, which can be quite big. So MCUNet v2 proposed this patch-based inference methodology, which breaks the memory bottleneck with patch-based inference. This is a 2-layer example. Every time we just compute a quarter of this feature map, we do it for the first layer and second layer and store it, materialize it in the third layer. So we are no longer doing it layer by layer, but we are calculating layer 1, 2, and then 2, 3, and then store it. Its partial result, that's only the top left corner. And then we do the top right corner for layer 1, 2, and layer 2, 3. And since after the downsampling, the feature map becomes much smaller, what we need to hold equal to the total region, total area of this blue region, which is much smaller than these two, since they have much larger resolution. So let's see what is happening to the activation after we do such patch-based inference for the first couple of stages. Like immediately we can reduce the activation from here to here by using such patch-based inference. We cannot only do just 2x2 patch, we can also do like 3x3 patch. So this is the measured result for peak SRAM usage. So this per layer versus 2x2 patch versus 3x3 patch can be like 4 to 5 times smaller usage for this SRAM. And this is the memory saving when we are publishing this work in NeurIPS 2021. But that leads to a problem, right? Repeated computation, overlap the regions. For example, when we are computing these two patches as output, all this yellow region concerns this yellow output because of the receptive field. Remember, we talked about the receptive field. These input pixels all matters for this output pixel, and this blue part also matters for this blue part. That is for one layer, because here we have stride of 2, which makes the receptive field quite large. If we backtrack another layer using this 3x3 convolution stride equal to 1, the receptive field gets even larger, and the overlapped region is also larger, right? So we are using this 2x2 patch. We have to compute this area twice for this halo region. And how do we solve that? And first, we need to figure out what is the reason. Okay? The reason is the receptive field grows when we are going back, especially when we are having strided convolution. And the overhead is actually 10% for the total amount of computing. So compared with 4x memory saving, this might be negligible, but we want to do it perfectly to completely remove this 10% of MAC increase due to those halo regions. And what do we do here? So we want to reduce the receptive field in the first couple of stages when we are doing patch-based inference, and increase the receptive field in the later stages when we are doing the layer by layer inference. Okay, for the patch by patch inference, we reduce the receptive field. For layer by layer inference, we increase the receptive field. As you can see, we removed one of the 3x3 convolution. Okay, we replaced that with 1x1 convolution, which has smaller receptive field than 3x3. And here we inserted one more 3x3 convolution in the patch-based later stages. So overall, the total receptive field stays the same and accuracy stays the same. But here, the number of halo region becomes much smaller. Okay, so by putting them together, we can have this MCUNet v2 combining this neural architecture search versus inference scheduling using this per patch based inference. And here we have several design knobs to search, including the number of layers, number of channels, the kernel size for the neural architecture search part. And for the inference scheduling part, we have to search the number of patches, number of layers for patch-based inference, usually the first couple of layers, but how many, we have to search that, and other knobs from the TinyEngine, which we are going to talk about in the next lecture. And here brings the result. This is our 2019 result. This is 2020 result. This is 2021. Europe's 2021 result. Every year we've been pushing the forward, pushing the frontier. First reduce the memory by twice, another 4x, which is pretty exciting. Now we can do person detection, visual wake words using only 30 kilobytes of SRAM with 90% accuracy. Or if you have 62 kilobytes, you can reach 93% of accuracy detecting person versus no person. Like you can try to spot whether there is someone in your room for safety. And from MCUNet to MCUNet v2, by using this kind of patch-based inference approach, we can make the memory 4x smaller. From this point to this point, okay, previously it was 120 kilobytes, now it's only 30 kilobytes. We can also do ImageNet scale classification. Like previously, we can never imagine you can do ImageNet scale classification on tiny microcontrollers, but now we make it. From MCUNet to MCUNet v2. First of all, MCUNet already make a big improvement compared with MobileNet v2. From 40 to 60, like 10% increase on ImageNet, is considered pretty amazing. And then MCUNet v2 continue made another more than 4% accuracy improvement, and 3% accuracy improvement on different microcontrollers. So thanks to this once-for-all network, we can easily design the specialized different neural network architecture to fit different hardware constraints. Like here is 256 kilobyte or 320 kilobyte. So without this once-for-all network, you have to retrain, redesign every time. But now you just have the same once-for-all network as the SuperNet. And then you can subsample different subnetworks from it. So we can not only do classification, but also detection on microcontrollers. This is using only 320 kilobytes of SRAM, but we can drastically improve the MAP, the mean average precision on these detection tasks. So this is the overall MCUNet v2 architecture, consisting of starting with a resolution of 160 by 160. We can fit actually pretty large resolution using patch-based inference. And then we downsample that using several mobile conv layers with different kernel sizes. So the legend is a combination of expansion ratio and then kernel size by kernel size. Here are some insights. In the per patch-based inference, okay, so the kernel size is pretty small, either 3x3 or 1x1. And the reason here is try to reduce the receptive field here and reduce this overlap, this halo region, reduce this spatial overlapping. And the expansion ratio in the middle stage is pretty small to reduce the peak memory, because in middle stage, the resolution is still relatively high until you go to the late stage where the resolution is pretty low, then you can have wider resolution, wider neural network with lower resolution. And then we put larger input resolution compared with prior work so that we can detect smaller people, smaller objects, like using even 160. Like previous generation is only using 128. All right, with that, let's take a break. And then before we jump into the applications of TinyML. Welcome back. Now is the fun part. We're going to see some applications of TinyML. Our TA G just bring some amazing demos. We can pass you around and so you can have a look at how this works in real world. We're going to cover 3 applications of TinyML, from the vision to audio to time series and anomaly detection. And let's start with image classification. This is a demo by Google previously using a microcontroller. They can recognize oranges, apples, and also bananas. It is moving pretty quickly. I can tell you the probability of these different fruits. This is a pretty simple task, pretty fun, but it's also limited. With MCUNet, we can expand it to like 1,000 class classification with MobileNet level accuracy, which is pretty amazing. So this is the accuracy before our work. MobileNet from Google, CMCN from ARM, the best achievable accuracy on this 512 kilobyte of SRAM and 2 megabytes of flash. This is a microcontroller by STM32H743, a pretty high-end microcontroller. The best previous prior art is 53.8% top-line accuracy. But with MCUNet, we boosted to 70%. Every 1% matters for ImageNet. This is like double-digit improvement, which is the first to achieve more than 70% ImageNet accuracy on commercial microcontrollers. Another amazing thing is that we can easily design specialized networks for diverse constraints, from 256 kilobyte to 20 kilobyte, 12 kilobyte, and the flash can range from like 1 megabyte to 2 megabyte. And each time we don't have to retrain the model, since we can use this once-for-all approach to use the same super network, the same once-for-all network, and sample different subnetworks for different memory constraints. And as we did the exercise earlier, the relationship between the flash and also the SRAM with respect to the number of channel and also the number of resolution is very complicated. Therefore, rather than hand calculate each case, like we went through that exercise, we use this evolutionary search to automatically find the best configuration, as you did in the homework with evolutionary search. So one application would be the visual wake-words. It's like the vision counterpart of OK Google, Hey Siri, those kind of stuff. For example, we can only enable the face recognition when the person is in front of the camera, or give you some alarm when you're not at home, but some strangers breaks into your home. And so here we deployed it on this microcontroller that is battery powered. There's a light on it. When it's green, it's showing the home is safe. At least it's not seeing any person. When it turns red, as it sees a person. So I'll pass it around for you to take a look. This microcontroller is basically this one, STM32H743, which has 512 kilobyte of SRAM and 2 megabytes of flash. This is another demo we recorded in building 36 in the elevator we have this microcontroller over there. When there's person, it's red. And if the person leaves, it will, when there's no person, it's green. When there's person, it's red. Actually, it's pretty instant. And there is some certain direction you have to be careful about. One direction, I believe there's an arrow on the microcontroller. I have to follow that arrow to make it work. Not only classification, but also object detection. Okay, so object detection is very sensitive to the input resolution, since we need to make a denser prediction. So this kind of patch-based inference is very helpful because it can fit a larger resolution by using this patch-based inference and breaks this memory bottleneck. This figure shows the accuracy measured with mean average precision versus image resolution. You can see as we start with a high resolution, gradually we reduce the resolution. Actually, there is a pretty big degrade of accuracy. So the resolution matters a lot for these detection tasks compared with classification tasks. With classification tasks, degradation is not that severe, but for this detection task, the degradation is actually pretty severe, showing that the detection applications are more sensitive to the resolution. Therefore, making it more important to use like MCUNet v2, is patch-based methods to reduce the increase resolution we can fit. This is a demo for detection, detecting the face versus the mask versus no mask. And here we can do not only a single person, but also we can do multi-person, mask, no mask, blue, green versus red, very real time. On the right-hand side is showing the person detection, detecting person sitting right here, sitting pretty far, can still be detected versus the people walking around. I also have the demo here for you to play with. So this one is a person detection demo. You can point it to someone, and then here is an arrow showing you have to use it in this way rather than this way, otherwise it will not work. So follow this arrow, I'll pass it around for you to play with.
The reason that you have to hold it because we're able to
not due to the hardware, but due to the training data. We didn't flip do the rotation that aggressively. And here is the face and mask detection. And also follow this direction, and I'll pass it around. Or I have some masks and play with. It will change the color when it detects someone is wearing the mask versus not wearing the mask. You have to put the mask over the face, but it's hard to see because you cannot see yourself. Maybe you have to work in pairs, looking at each other wearing face mask versus not wearing face mask. Yeah, I'll leave you some time to play with it. Yeah, we have another demo here to show why higher input resolution is important. With this patch-based inference, we can enable a larger resolution. Compared with previous methods, like there are some false predictions on the hand, but now we no longer have those false predictions, or if the face is very tilted, it cannot be detected before, but now we can still detect it. Versus this one, this guy wasn't detected due to the face is tilted, but still we can well detect it, and a lot less false positives since we have a higher resolution, and also we can find those details. So patch-based inference. Amazing part is we can not only do inference, but also do training on microcontroller. So this is the lecture we are going to learn in the next part of the chapter, where we can, let's see if this is a video. Okay, this is the video. So we have two buttons. Okay, so we can give it an input, manually label it by pressing the button, like pressing the green button for the orange and pressing the red button for the banana. Initially, cannot distinguish between orange and banana, so after we manually feed it with some clicks, with some piece of the data, it should be automatically classify it after a few iterations. There it goes. You can change the color when it recognizes the banana versus the orange.
Does this then work?
Oh, we have a demo for you to try. Feel free to give it some challenging tasks. So we 3D printed these two buttons and stick it to this microcontroller. You can see there is a rectangle on the top right corner. If you press two different buttons, and it will show if it is as recognized or not. You can feel free to pass around, look at two different objects and press these two buttons, try to distinguish different subjects. There's no reset button. So from student to student, you have to unplug it and then plug it back again to reset it. So this is like a prototype. So let me hand you some objects so that you can play with. Maybe this, or you can use whatever you have, try to distinguish. Don't forget to reset it by unplug the power, otherwise, or maybe it can still recognize new objects, but continue training and forgetting, training and forgetting. Or you can try to break it by, not physically break it, but algorithmically showing some similar like colors, both black colors, see if it can still be detected. Maybe this one is too easy. You can simply classify them by the color. One is yellow, the other is orange. But we didn't overfit by the color, but it's purely initialized from ImageNet pre-trained model, then fine-tuned it. Fine-tuning is actually a lot more challenging than just run inference, because you not only have to do the forward pass, but also the backward pass. Not only the activation, but also the gradient. It's a lot more complicated, but we are going to cover this in a few weeks. All right, so while we are playing, we can slowly progress to tiny audio. Right? So speech recognition and also the keyword spotting is very popular, right? Hey Siri, Alexa, those kind of applications. Like it's responding, it's working, which is pretty good. So that's audio keyword, right? That's a perfect demo. And also keyword spotting, other keyword spotting tasks, speech recognition tasks. GPT-4 already included that. You can talk to the latest ChatGPT using speech interaction. But having them on this edge device is quite helpful. It's real time, doesn't leak your information, and give a perfect interaction, human-machine interaction experience. So how do we deal with those audio data? So the audio data, the input is the overlapping frames of length L with stride S. So totally there are this amount of frames in total. we can use either human engineered features or using the neural networks to extract those features. And all together, we put them in this spectral, this frequency spectrum map, which is similar to an image. It has two dimensions. One is time, the other is a frequency. And the value is the strength given that time and given that particular frequency. And we can treat it exactly as a 2D image. Use the CNNs that we talk about to convolve to convolution on this map. And later we can classify whether it's yes or no or on or off, those kind of speech commands. So people find the CNN architecture using convolution architecture can outperform just using those FC layers. So this spectral representation of speech have strong correlations in time and frequency, right? So that's ignored by DNNs, but CNNs can capture those locality. The similar time, similar frequency, the signal has locality, just like image. So this is showing that DNN methods versus the CNN-based methods can perform quite well on these speech tasks. And actually, MCUNet also support this Google this is Google keyword spotting data set. So this is the latency versus the accuracy, including MCUNet. This is MoveNet v2, proxyless NAS. Some of them are already out of memory, but here we can be either like 2% higher accuracy using similar latency, or very similar accuracy, but 2.8 times faster. On the right-hand side, this MCUNet can fit within this 256 kilobyte of memory constraint, while being 4.1 times smaller compared with this MoveNet v2 based model. So it's showing it's possible to apply this software and system algorithm and system co-design on this speech command dataset, Google speech command dataset. It includes lots of different commands to recognize. And finally, time series and also anomaly detection. So here we have some normal versus abnormal capsule, good capsule, a bad capsule with a crack here, a good nut, a bad nut here, some bad part here. So we on the pipeline in the factory, most of the time we want to have this automated approach to distinguish between the normal versus abnormal cases, which is helpful for video surveillance, healthcare, prevent the fraud, and also adversary attacks. So very commonly used technique for such anomaly detection is to use autoencoders. So what is an autoencoder? Autoencoder is a neural net that the output is the input. And we feed it with the input. It tries to reconstruct this input. Okay, it has two components, the encoder and also the decoder. So the encoder tries to compress this high dimensional input into a lower dimensional code vector. Okay, this is like long, pretty big dimension. This is a much smaller dimension. So the code vector is something in the middle, which is the abstraction of the input. And the job of the decoder is try to reconstruct this input by using this low dimensional compressed code vector to reconstruct the output from the code vector. And we try to match the input and output. So we train it on a certain data set. So if the new data follows the distribution of that data set, we should be able to reconstruct the input really well. But if this is an abnormal scenario, falls outside this normal distribution, this autoencoder can no longer reconstruct this input. And as a result, if you encounter those abnormal samples, the X prime will be quite different from X. So by examining the difference between the input and the output, you can tell whether this is a normal or abnormal scenario. So here is an example. We try to feed it with a input image, and then this is the reconstructed image. It actually looks very similar, very similar. We try to minimize this reconstruction error. So during training, do we need any label? No, right? We don't need any label because we are constructing the loss function here is just the difference between the input and the output pixel-wise. So no loss, no label is needed. It's purely self-supervised, try to learn itself. And when we are doing it for the test case, feeding with live data, and then try to see what is the reconstruction error. If the error is larger than the threshold, it means it doesn't follow our training data's distribution. We can flag it as an anomaly input. So therefore, it's unsupervised. We don't need any label for training, which is really good. But it's data specific, right? So it can meaningfully compress a subset of data, a specific domain of data, like images, for example, digits versus other kind of image. They are completely different. They might be able to only encode a certain domain of data. That may be lossy, so the output and the input, they cannot be exactly the same. Even the normal data might have some reconstruction error. So we have to carefully fine-tune to tune this threshold to avoid having these false positives and false negatives. So false positive is saying it's actually a good normal data, but we flag it as abnormal, right? So we want to avoid those cases. Or false negative, it should have been flagged as abnormal data, but it was flagged as normal data. So here, one of our MCUNet student did a thesis with me to detect this fan anomaly on a Arduino Nano 33 BLE Sense, this kind of microcontroller. The hardware constraint has only 256 kilobytes of SRAM, 1 megabyte of flash. So here we are trying to poke it, and it's going to show, you can tell from the light, the normal case versus the abnormal case. There is actually a yellow light right here. The yellow light light up when it's abnormal, and it's going to disappear when it's normal case. Now it's yellow. Now it disappeared. And now it's yellow. Right. Yep. Oh, so here is the accelerometer, the XYZ, different directions. You see it again. Oops. The yellow part is here. It's a bit noisy, so let's watch it offline. All right, so in summary, today we learned about TinyML, the challenges of TinyML, the small memory size, orders of magnitude from GPUs and mobile phones, and how do we design neural networks to fit many different dimensions, from the weight to the activations. And in the future, we are going to talk about gradient when we talk about on-device training, and also the SRAM, the flash, different aspects, and also the design space. How do we design the design space with the resolution, with the channel number, with multiplier, etc. and also introduce this patch-based inference to drastically reduce the bottleneck of the activation in the first couple of stages, and introduce several applications, videos, audios, and time series, and show you some demos. All right, I think that's all for today's lecture. Next lecture, we are going to cover the inference engine part, which is the foundation for our lab 4 to let you learn about how to write efficient kernels. We don't have this. This is from last year's lecture. So that's all for today's lecture. Oh, feel free to continue play with the microcontrollers. I will stay here for a while to help you answer questions. And we have office hour today as well.